Hello, and welcome to your first Support Vector Machine lecture. Support vector machines are classification models, which means they predict a group or a category. Over the course of the next two lectures, we're actually going to talk about three related models: maximal margin classifiers, support vector classifiers, and then finally support vector machines. Each of these models makes an improvement on the previous one. However, they all have one very important thing in common. They use hyperplanes in order to divide space so that we can distinguish between two groups of data points. First, let's start with a little terminology. What is a hyperplane? If you ever read any books or articles or even watch any videos about support vector machines, you're probably going to hear the term flat affine subspace, which is a very fancy way of saying a hyperplane. Let's go through what each of these terms mean so that you understand what people are trying to communicate to you when they use this phrase. The word flat basically just means that the hyperplane is not curved. It's going to be a straight either line or hyperplane. That means that in each direction, it either increases or decreases constantly. Affine is just a fancy way of saying that the hyperplane or line that we're working with doesn't have to pass through the origin 0, 0. And the word subspace just is a fancy way of saying a subset of vectors in a larger vector space. For those of you that have taken a class that covers subspaces, hopefully this is review, but for those of you that haven't, let's look at an example. In 2 dimensions, our subspace is a one-dimensional line. In 3 dimensions, our subspace is a 2-dimensional plane. So you can see that anytime we have a subspace, at least for our purposes, it's going to be an n-1 dimensional object. In 2 dimensions, that's a 1-dimensional line. In 3 dimensions, that's a 2-dimensional hyperplane. Just as a quick check, pause the video and look at these 3 pictures. Which of these represent flat affine subspaces? Alright, hopefully you guessed that the left-hand picture is the only one that is a flat affine subspace. The second picture is not flat, and actually neither is the third picture, nor is it a subspace. So basically we can expect, whether it's in 2 dimensions or more, that we have straight lines or hyperplanes. Alright, now that we've gotten some of that terminology out of the way, let's talk about why we care so much about these hyperplanes in the first place. Hyperplanes divide spaces in half. In all 3 of these examples, you can see that our hyperplane, aka a line in this 2-dimensional case, divides the space that we have into 2 sections. We have sections above the line represented with these pink dots, and we have the section below the line represented with these blue triangles. The equation of our hyperplanes can be written like this: W transpose, which is our weights, times our input values, which are stored in the vector x, plus an intercept or bias term. When we set that equation equal to 0, we get all of the points on our hyperplane, or in this case, a line. By the way, this notation is just another way of writing this. So this W transpose x plus b is basically the same thing as writing an intercept plus a weight times an input plus another weight times an input, etc., and then setting that value equal to 0. This notation is just a little easier, especially if we work with a lot of different input variables and weights. So why do we care about these hyperplanes that split our spaces in half? Well, because it'll help us classify between 2 groups of points. If we're going to use this hyperplane as a classifier, we can classify all the data points above the line as one category and all the data points below the line as another category. Unlike some previous examples in data science, we're going to classify data points that are positive with a 1 and data points that are in our negative class as a -1 instead of a 0, which we've used in previous cases. So we take our data points and we plug them into this formula. If the value of this formula is above 0, it's going to be in this region, and we'll classify that as a positive case. Remember, if this formula equals exactly 0, that means that the data point is actually on the line precisely. If we take this formula and plug it in and our data point has a value less than 0, that means it's below the hyperplane, and we'll classify it as a negative value. So now we have a way to classify data points. If we plug it into this formula and we get a value greater than 0, we classify it as positive, or a 1. If we get a value and we plug it in and it has a value less than 0, then we classify it as a negative case or a negative one. Now, I want to simplify these two formulas into one. In order to do that, let's do a little algebra. So to combine these two formulas, we're going to do something interesting. We are going to take the target value, which is going to be +1 if the case is a positive case, and -1 if the case is a negative case. And we are going to multiply it by that formula W transpose xn plus b. Now, when the target value is 1, and we multiply by it, it just leaves everything the same. So we get our formula is greater than 0. When the value of our target is a negative class, or -1, when we multiply it, this part stays the same. However, we change this less than sign to a greater than sign because we're multiplying by a negative number. And oh, those actually look really similar. It turns out we can write those two formulas as a single formula. The target variable, 1 for positive classes and -1 for negative classes, times our formula is always going to be greater than 0. This implies that all of our positive cases must be above the line and all of our negative cases must be below the line. So we've just seen that we can use hyperplanes to classify data points into a positive group and a negative group. For example, here we have two groups of data. The dark, larger data points are our actual data, and the background colors represent points in our graph that are either going to be classified as positive if they're above the line, or negative if they're below the line. This hyperplane perfectly divides our two groups of data. All of the positive cases are above and all the negative cases are below. So if we ever want to classify a new data point that we don't know the group of, we can just see, does it occur above or below this hyperplane, and classify it as positive if it's above and negative if it's below. So we just saw why hyperplanes are really useful for classifying data points as positive or negative, but we have a little bit of a problem. If a hyperplane like the one over here exists that perfectly divides between the positive class and the negative class, then by definition, there are an infinite number of hyperplanes that could do the exact same thing. For instance, on the right-hand side, you can see that there are a bunch of different hyperplanes with their slopes or intercepts just changed very slightly that can all divide between our positive and our negative classes. So if there's an infinite number of hyperplanes, how do we choose the best one? Enter the maximal margin classifier, the first of our models that we'll talk about. We just said that we have a problem. If a hyperplane exists that can perfectly divide between positive and negative cases, by definition there will be an infinite number of hyperplanes that could do the same thing. So we have a problem. Which one do we choose? Well, the maximal margin classifier says we should choose the one that is furthest from the training examples. If you look at these three examples on the bottom, you can see the same exact data with different hyperplanes dividing our two groups. For each of them, we show the distance between the hyperplane and the closest data point. As our hyperplane moves, the data point that is the closest will change, and the distance between the hyperplane and the closest data point will also change. Of these three examples, this hyperplane has the furthest closest distance. That means the distance between the hyperplane and the next closest point is as far as possible. And that's how we choose which hyperplane to use. For maximal margin classifiers, we want to maximize the margin, which is the distance between any data points and the hyperplane on either side. One interesting thing that we'll talk about a little more later is, if you notice, you could take any of these data points that are not in or on the margin and you could move them around and nothing would actually change about where our hyperplane is, because all it's looking at is making sure that it maximizes the closest distance between a data point and the hyperplane. So as long as you don't move our data point into the margin or even onto the incorrect side of the hyperplane, it will have no effect on what the hyperplane actually is. The data points that do have an effect are the ones that are on the margin, and these are called the support vectors. Our support vectors are the only data points in the data set that actually impact where that hyperplane will go. All of the other data points have essentially no influence. All right, let's talk a little bit about math. Now, before we start, I just want to acknowledge, I know that the notation can be a little overwhelming. I'll try and pause at each point that we have to make sure that you understand the concepts that we're trying to enforce by going over this math. First, just for reference, this is the formula to find the distance between a data point and a hyperplane. Remember, a maximal margin classifier wants the closest data point to be as far away from possible from the hyperplane. In other words, we want the largest margin possible. Here you can see that this is just this distance formula rewritten. This is just saying that we're going to find the distance between every data point and the hyperplane, and then figure out which of those data points are the closest to the hyperplane. That's what this min does. It's trying to find the closest data point to the hyperplane. And then of course, because we're trying to maximize our margin, we are going to choose weights and biases that maximize this closest distance. So even though this is a bit of a mouthful, you can think of this as maximizing the minimum distance between a hyperplane and the closest data point. However, because we're required to have all of the positive cases above the line and all the negative cases below the line, we have this constraint that we talked about earlier, that our target variable, either 1 for positive cases or -1 for negative cases, times this formula always has to be greater than or equal to 1. Data points where it's equal to 1 are the ones that are actually on the margin, and data points for which this is greater than 1 are ones that are on the correct side of the hyperplane outside of the margin. Now, because the math is a little bit easier, instead of maximizing this function, we are going to minimize this function, which is essentially the same thing. So again, our goal is to minimize this function subject to the fact that this has to be true for every data point. This constraint is important because we could choose a line that's like off the graph right here, and the distance between this line and the closest data point is huge. But this is also a really bad classifier. Remember, we want this hyperplane to divide our two groups of data points, and this one completely fails at that. By enforcing this constraint, we ensure that our hyperplane actually will divide our positive cases from our negative cases. All right, so now we're going to talk about constrained optimization. And there's going to be some math, but again, I promise we'll stop and talk about the concepts that are important as we go through the math. First, let's take a step back and figure out what we're actually doing. Constrained optimization is the idea that we have two things. A function that we would like to optimize. Optimize means just to find the minimum or the maximum of the function. But we have a constraint that we have to follow while minimizing or maximizing that function. For instance, we might want to maximize the function 2x plus y, subject to the constraint that x squared plus y squared equals 1. So we want to figure out how big or small we can get our function f while still operating under the constraint that x squared plus y squared has to equal 1. Well, it turns out that the minima and maxima, or optima, of the function occurs when the function and the constraint are tangent to each other. You can see this visually on the graph. Here is the maximum of our function, and here is the minimum of our function, subject to our constraints. So if we want to find the minima or the maxima of our function subject to a constraint, we need to find where that function is tangent to the constraint. Now, you can just take my word for this, but when two functions are tangent to each other, it means that their gradients are parallel. You can see an example of this here, where the gradient of our function is basically the same line as the gradient of our constraint, except it's scaled. In function terms, we can write it like this. The gradient of our function is equal to some scalar value that's just like a number, like 1 or 2.7, times the gradient of our constraint. If we can find the values that make this equation true, we find the minima and the maxima of our function subject to our constraint. In order to do this, we have to find the gradient of f and the gradient of x. Here, I've done it for you. I don't expect you to be able to calculate these partial derivatives, just understand that we're calculating the gradient. Now we're going to plug them into our formula. We know that the gradient of f is going to be equal to some scalar value lambda times the gradient of our constraint. So we just set them up in this formula. And I'm not going to make you do the math, but when you solve for these values, you find these 2 points, the minimum and the maximum of our function subject to our constraint. So to review, if we have a function that we want to optimize and a constraint that we have to adhere to, we need to find where that function and the constraint are tangent. In order to do that, we use the gradients and we just solve for these two values. Now let's talk a little bit about a Lagrangian. Lagrangians are a way to do constrained optimization like we just did by hand before, but it makes the math slightly easier. The Lagrangian rewrites our function and constraint in this form, adding the term lambda, which is called the Lagrange multiplier. This basically takes our function and subtracts lambda times our constraint minus the value it's constrained by, in other words, this value. For the example we did by hand before, this would be its Lagrangian form. We have our function minus our Lagrange multiplier times our constraint minus the value it is constrained with. Now, why would we rewrite these two perfectly reasonable functions into one bigger function? Well, it turns out it's because it makes the math a little bit easier. Well, at least if you understand partial derivatives. When we take the partial derivative of our Lagrangian with respect to each of these three variables, some interesting things pop out. For instance, and I don't expect you to be able to take these partial derivatives by hand, when we take the partial derivative of the Lagrangian with respect to our Lagrange multiplier, this pops out, negative gxy plus c. And when we set that equal to 0, that only happens when g of xy equals c. And oh, look, that was our constraint. Interesting. Next, if we do the same thing with the partial derivative with respect to x and set that equal to 0, another familiar thing pops out. This looks a lot like this function. And that's because it is. And without spoiling anything, if you plug in the partial derivative of the Lagrangian with respect to y, the same thing pops out, but with y. So basically, the Lagrangian is a way to rewrite our function and our constraint, where if we set its partial derivatives to 0, or in other words, its gradient to 0, we solve for the values that we wanted before. Interestingly, this Lagrange multiplier that we find tells us how changing the constraint value of our constraint would change the possible minima and maxima for our function. All right, that was a lot of information about constrained optimization. So let's really quickly go through what the main points were. If we have a function that we want to optimize, aka find the minima and maxima of, subject to some constraint that we have to stick to, we need to find where the function and the constraint are tangent to each other. That would be at these points. For example, say you want to maximize the profit of your company, but you have to stick to the constraint of a budget for labor and materials. Next, if we want to find where two functions are tangent, we need to find where their gradients are pointed in the same direction. To do that, we can solve this equation, which says the gradient of our function is equal to some number times the gradient of our constraint. Last but not least, we can use a Lagrangian in order to find all these values by plugging them into a single function and setting that function's gradients to 0. So why did we just spend our time talking about constrained optimization and doing some potentially confusing math? Well, it's because we can use constrained optimization in order to find a hyperplane for our maximal margin classifier and later down the road for our support vector machine. Remember from before that we have a value that we are trying to minimize, and we have a constraint for each data point. That is, every single data point has to be on the correct side of the hyperplane, with all the positive examples above the hyperplane and all the negative examples below the hyperplane. We can use a Lagrangian in order to do this. For instance, this would be the formulation of the Lagrangian for this function with this constraint. Because technically we have one constraint per data point, we're actually taking the sum of all of these constraints rather than having one big constraint like we did before. Here, an is the Lagrange multiplier for the constraint imposed for data point n. That is, that it is on the correct side of the hyperplane. Now, I'm not going to make you do any of the math, but there are resources in our resources page that are linked if you want to follow along. However, I do want to show you some cool things that pop out when we let other people do the math for us. First of all, when we solve for w and we plug that back into our Lagrangian, something really interesting happens. Remember, Lagrange multipliers are just numbers that are greater than 0, and our target values, 1 for positive cases and -1 for negative cases, are also just scalar values. So that means in order to find the hyperplane, it really only relies on just some random numbers and then the dot product between two data points. This will come up later and is very useful. Next, from that we can derive that this is the formula to classify a new data point x. So if we have a new data point and we want to classify whether we think it's a positive case or a negative case, we just plug it into this formula. And of course, we are subject to these constraints. Now this last constraint is the most interesting one. This says that our Lagrange multiplier times this formula right here has to equal 0 for every single data point. Now because we have a value multiplied by another value, this can only be 0 when one or both of these is 0. That means that either the Lagrange multiplier must be 0 or this value must be 0. And when is that value 0 again? Oh, it's for vectors that are exactly on the margin. This reinforces that point that we talked about earlier. Only the data points that are on the margin determine where the hyperplane is. All of the other data points don't really matter as long as we don't move them so that they're on the wrong side of the hyperplane. This constraint is just a very mathematical way to prove that point. Either data points have no influence on the hyperplane because their Lagrangian is 0, or they're on the margin and they do have an influence. By the way, the fact that only a few support vectors influence where the hyperplane is makes support vector machines and maximal margin classifiers very computationally efficient because really only a few data points matter. All right, so we've done a lot of math and we've talked about maximal margin classifiers. Remember, maximal margin classifiers find a hyperplane that perfectly divides our positive cases from our negative cases. However, we need to improve on this model because real life is never so clean that we can perfectly classify between our positive and negative cases. Often our groups of data will overlap and they're not linearly separable. There's not a line that we could draw that would perfectly classify positives as positives and negatives as negatives. It's also the case that even if we could perfectly classify positives and negatives, we might not want to. For instance, if we look at the classifier on the left compared to the one on the right, we can see that the addition of this single, pretty far out there, maybe outlier point is changing the hyperplane a ton. And maybe we don't want a single point to have that much influence. Enter the support vector classifier. The support vector classifier relaxes that constraint. The data points either have to be on or outside of the margins. Instead, support vector classifiers allow data points like this 8 and this 1 to actually be inside the margin. In fact, data points can not only be inside the margin, they could be on the entirely incorrect side of the hyperplane. By relaxing this constraint, the data points have to be on or far away from the margin. Support vector classifiers allow us to use a hyperplane to classify data that is not linearly separable. Mathematically, the way we do this is with the introduction of something called a slack variable, which are these little curly Q guys right here. The slack variable basically represents an error. So data points that are on the correct side of the hyperplane and outside of our margin are data points that are being very confidently classified by our support vector machine. So data points that are in this region have a slack variable of 0. Of course, this would also be true for the other group of points on this side. Data points that are violating the margin but are on the right side of the hyperplane have a small slack variable, less than 1. That occurs in this region right here. While technically our support vector classifier is correctly classifying these data points, it's not as confident about its classification, so we want to penalize that a little bit. And for data points that are on the completely wrong side of the hyperplane, like this one right here, the slack variable will have a value greater than 1. With the introduction of these slack variables, we're also going to change the function that we're trying to optimize, as well as the constraint. Whereas previously we tried to minimize this value, Now we're adding a constraint on how big the sum of the different slack variables can be. This hyperparameter C basically controls how large of a cost it is to have a slack variable that is greater than 0. Similarly, whereas before we had a constraint that required all of our data points to be on or outside of the margin, our new constraint allows some data points to violate the margin or even be on the wrong side of the hyperplane by adding in this slack variable term. Now, back to that hyperparameter C. Remember, the hyperparameter C controls how big of a penalty we're going to give to slack variables that are greater than 0. When we have large values of C, the penalty for having a slack variable greater than 0 is huge. This leads to less regularization of our model and narrower margins overall. This is because it's so costly to have a slack variable greater than 0 that we try and find a hyperplane that can perfectly separate our data. In terms of the bias variance trade-off, this leads us prone to overfitting. This should make sense intuitively. When it's costly to have a slack variable that is greater than 0, we're going to have very narrow margins with very few support vectors. And remember, where the hyperplane is solely determined by your support vectors. The fewer support vectors you have means the fewer data points are influencing where that hyperplane is. On the other hand, when we have very small values of C, our model is more regularized and we tend to have wider margins. This is because it's not so costly anymore to have a slack variable that is greater than 0. In terms of the bias variance trade-off, this leads us to be prone to underfitting. Visually, you can see what happens here. On the top left corner, you can see that we have a very small value of C. The margins are so wide you can barely see them on the graph, and there's a ton of support vectors, those data points that are either on or inside the margin. As we go through the other images, you can see that the value of C is increasing, leading to narrower margins with fewer support vectors. Again, we'll typically choose C using something like hyperparameter tuning, but it's really helpful to intuitively know what it's controlling. All right, that's all I have for you. I will see you next time.